I will talk about briefly about translation quality assessment and what kinds of fundamental problems there are with this. And then Longhui wanted to take over and talk about how we did this in this for our study. Okay, so what is translation quality has been, well, a hot discussion for, I guess, for centuries maybe. And recently it has become very interesting also due to machine translation. Here is a definition from Alan Melby. He says that a quality translation should demonstrate the required accuracy and fluency for the audience and purpose and comply with all other negotiated specifications taking into account end user needs. Wow, that's a lot of terms, which, well, I guess it makes sense. It's a very comprehensive definition, but each of these terms raises further questions. So what should that mean, accuracy and fluency? Does it, so one answer could be it fills the communicative purposes required accuracy and fluency. The audience and purpose, what is the text supposed to accomplish? For whom is it and why is it? Who will read the text? Negotiated specification. There is lots of this discussion in post-editing specification and post-editing guidelines, which specify for whom this translation is and what the translation should look like and how much post-editing is needed, and also accounts for end-user needs. So here, these needs may override accuracy and fluency in different ways. So this is a whole complex area where every definition then asked for more definitions. But on a practical side, so people were talking about translation quality from translation studies, questions of hermeneutic linguistic theories. Computational linguists have investigated this and developed a number of automatic measures for for translation, mostly machine translation. These are reference-based, means that there is an assumed ideal or gold translation, one that should be approached or comes close to. And then there is also metrics without reference translations, such as feature engineering and so on. So we have different kinds of automated translation evaluation computational methods for translation assessment. And then, of course, we have also manual assessment of translations. And here we have, we can assess the translation quality on a word or a sentence level, or even on a whole text. One could just give a score for these different kinds of units. And then the most precise, perhaps, is an error taxonomy, means that one annotates what are the errors that are visible in the translation. And there have been a large number of error taxonomies too, and here are just 3. And the MQM, that's what we are going to talk about a little bit later, is a multidimensional quality matrix, which tries to integrate a number of different kinds of taxonomies. But basically, the problem is, however you define these criteria, here is an example. For instance, you could have just 2 criteria, fluency and accuracy, where accuracy relates to how well the meaning of the source is transferred into the target text. That would be accuracy, and assumed to be independent from there is somehow fluency. How well does can the text be read? How well does it fit the required target language constraints? So if we assume that we have these kinds of taxonomy, means we have two types of errors, and each can then be we have 5 different points, levels of fluent or non-fluent or meaning transfer in these two. Yes, so from all meaning is transferred to none, from flawless English to completely incomprehensible. Seems to be clear, such a kind of a taxonomy, but if we ask evaluators to evaluate texts based on this, we may see something like this. So this is from 2006 evaluation of machine translation, I assume. And then we see that different evaluators with the same taxonomy have very different kinds of distributions of scores. So this person here likes to evaluate all the most of the translation with score number 2. So you can see very different distributions of scores here. This evaluator likes to give a 5, and then we have this kind of staircase here distribution. Those people here have a more like flat, even distribution. So we can see that basically this is reflects the big problem in translation evaluation, namely that evaluators do not agree on the scores. And there have been a large number of attempts to go about this, but I think this is basically an unresolved kind of a problem. So one of the attempts to address this is this MQM, multi-dimensional quality metric. And this was an initiative about 10 years ago, started here at from EU, and I think one of the main drivers was even from Saarbrücken, where I'm now from DFKI, and Hans Usgereit and his group, who had the idea to integrate various different taxonomies into one kind of big network of scores that I want to talk about. Is everything okay with the recording and with the, yeah, okay. Okay, so those people then, it was a group of people here from EU in an EU project, or even in a couple of EU projects, who started this this multidimensional quality metric to integrate various error taxonomies, and it's designed for professional and for manual annotation, but it has also been used for automatic annotation. It can be customized to needs, and it's available for free, and it has a very many websites and explanations of the different error codes, so that the idea would be to have some kind of a standard of the terminology and some kind of integration of the different approaches. Here is one layout for this MQM, which has here these 3 different kinds of categories. So in the middle you have issue type. So we have an error, right? We have an issue in a translation, and this issue can be of type accuracy. So it can be an accuracy error, a fluency issue, or here in this taxonomy, a verity error. And the fluency then, as already previously said, relates to the language, to the fluency of the target language. Accuracy, how well the meaning is transferred into the target language, and here the verity is whether the content is appropriate, more or less appropriate, whether it's complete, whether it fits the legal requirement, and so on. And as you can see on this picture here, it's a kind of a hierarchical organization. So we have in the middle, we have an error. So there is an issue in the text. And then we can say, okay, so what kind of issue is it? And is it accuracy, fluency, verity? And then we can go down in this tree and then decide or look into whether it's a mistranslation, omission, addition, and so on. So this is one type of factorizing this taxonomy. Here is another one where we have a number of more top level errors and a subset of the of the deeper branches and so on. And the overall taxonomy looks something like this, quite complex, where we have a couple of design here, internationalization, then we have fluency here, and then we have inside a quite deep embedded here branching factors where we can then cluster errors in different ways or specify errors in different ways. And I guess it's the idea is that this whole system is open. If you have certain issues, you may find somehow one of these main categories and then go down and maybe add further branches and specify your certain error types. But the idea is that people agree on basically this terminology and also the on this terminology and the branching and so on, so that these error types could be communicated between different groups and different participants. You don't not only have this taxonomy, but also a decision tree. So how to figure out whether you see something in a text, in a translation, which error it is, and they have designed a decision tree. So in the beginning, you start on the top left, and then you try to figure out whether it's a fluency error or an accuracy error, fluency error or accuracy error first. And then you have these questions, and you ask yourself, is it this kind of error or is this kind of error? And then you go through this decision tree, and in the end, find your error that you would like to annotate. So this is about MQM, and as you can see, it can be customized in very different ways and for different purposes and so on. And what we have done in our study for this site interpretation, we had 3 error types. So here you see the taxonomy that we have used in this annotation. So we had 3 kinds of errors: accuracy, style, and fluency errors on 2 levels, minor and major errors. So each of those errors could be more or less severe. We had 3 annotators. They annotated the same text, and we wanted to look into the agreement between annotators. How well do they agree about the errors, not only whether there is an error, but also what type of errors. And then we aggregated those errors on the segment level and looked at the impact of attention patterns that we discussed yesterday, ear dominant, eye dominant, and ear eye dominant, balanced interpreters. Okay, and this is my part, and I will now give over to Longhui, who I think should be there.
Yesterday, also someone has asked, do we have any quality assessment about our data set, or do we assess the interpreter's performance for our study? Yes, we did. So here is our second research question. After we talk about the visual input and audio input and how is the interpreter's attention patterns differ among individual idiosyncrasies. Now, today we want to go one step further to talk about how do different attention patterns affect the quality of simultaneous interpreting with text. Yeah, I actually added one slide before this. Is this annotation is done by Dr. Lucas Vieira, right? So we should thank for his support for our research. So this manual assessment is hired by Dr. Lucas Vieira and by the project Impetus, right?
Right.
Yes, and also this is the collaboration between CRITT and the University of Bristol. Yes, so here we can see this is the interface of Yawat. We have talked about it for maybe 2 times before this. And we can look into the manual assessment by the 3 annotators we hired for this study.
Sorry, go ahead.
Okay, yes. So we can look into this manual assessment by the three annotators that Lucas hired actually. And we have talked about how to customize your own error taxonomy on Yawat. So you can decide which errors you want. But for our study, we use an MQM adapted error taxonomy, as Michael just explained. And it's a very sophisticated error taxonomy. And we just took three types from this MQM decision tree, and we get accuracy, fluency, and style errors. And depending on the severity of the error issues, we also assign the minor error or major error to each error type we have annotated. So basically, we got 6 types of errors: accuracy minor, accuracy major, fluency minor, fluency major, style minor, and style major. And then we can see actually on the Yawat interface, we assigned different kinds of error with different colors. For example, we assign this accuracy errors depending on the error types. We assign accuracy errors as purple, fluency error as green, and style error as pink. And also, depending on the severity of the error, we have darker shade of errors, which is in dark purple, that is accuracy minor, and lighter shade of error, accuracy error will be major. Yeah, darker, darker accuracy error would be what in dark purple, and lighter accuracy error will be minor accuracy error. And also, there are also some errors that only occurred on one side of the text that we also talk about it in how to customize your own error taxonomy. Michael explained. So we call it mono error. So it only happens on one side. For example, if there are some omissions on the source text side, then it will be uh, in a pink, and when it's pink, it's a major omission. If it's in green, it's light omission. And it's on, if the error only appears on the target side, then it means it's addition by the translator. Then it will also be pink if it's major error. If it's green, it's light what? It's minor addition error. Yes. So here we have the same source text and target text by annotated by 3 different annotators. And we can see that for the same pair of source text and target text, the annotators can annotate very differently. For example, the source text is our shared interest in peace and security in our region and beyond make us natural partners. This is the source text. And the target text, I put the literal translation here for you to get an understanding if you don't know Chinese, which means our shared rights and interests of national security allow us to come to this meeting together. And this is one segment translated by our participant. And we can see that for annotator A, he assigned our translated into we as a style error here, and it's in light, means he thinks this is a minor style error. And here, this darker pink here, later in this segment, in our region and beyond, this only appears on one side of the text, which is the source text. This means the the annotator thinks this is a omission by the translator. So in Our Region and Beyond, he thinks this is a major omission by the translator. That is in pink and in only one side of the text. And here, Make Us Natural Partners was aligned with this light purple in the target text, which means to come to this meeting together. So the translator translate Make Us Natural Partners into to come to this meeting together. And the annotator A thinks this is a what? This is a minor accuracy error. And this is the decision by annotator A. And for the same source text and target text, we can even see from the color by the annotator assigned. These are annotated very differently by annotator B. Annotator B didn't think our into we is any error there. And then interest is translated into this rights and interest here. As you can see, both are in light purple, means he thinks it's a minor accuracy error. I think because he thinks there's some addition in the meaning of the translation. And then here we can see peace and security in Our Region and Beyond was aligned by the annotator to this one of means of national security. This very big chunk is translated into 3 characters in Chinese, which means of national security. And for this error, the annotator B thinks this is a major accuracy error because it's in dark purple. And then Make Us Natural Partners. The natural partners is also in dark purple, and it's aligned to the later part of the whole segment, which means the translator, the annotator aligned this natural partners to come to this meeting together. And he thinks this is also a major accuracy error. Yes, and for the annotator C, it's slightly different. He thinks also they first align, right? They first align the errors. So they think the peace and security is translated into national security in Chinese. And this was assigned as minor accuracy error. And in Our Region and Beyond was a omission, as annotator C thought, because it's only appeared on one side of the text and it's in dark pink. So the annotator C thinks in Our Region and Beyond was not translated by the translator, and he thinks this is a major omission error. And Make Us Natural Partners was aligned to allow us to come to this meeting together. And this was also assigned as a major accuracy error because it's in dark purple. As we can see, even for this very single segment, for the specific error types, the 3 annotators choose it very differently and aligned differently and assign the errors differently on the token level, right? And then next slide. Yes, so we did what? We did counted the word count of the source text and the target text. The source text has 16 words, and the target text in Chinese has only 12 words. And we counted by each arrow label. We have basically 5 arrow labels, and any arrow label is the overall arrow count of the other 5 types of errors. So we can see that for each single error and alignment, the three annotators choose very differently. But on the whole segment level, we can see the number of errors under each error label by the three annotators are very similar. For example, as we can see for the whole error count, A, B, and C annotators has annotated 16 errors, 18 errors, or 19 errors. Is very similar count. And then for accuracy error, we also see similar tendency. And also for fluency, style, and the only difference is about critical error and minor error. That happens a little bit differently among the three annotators. And next slide. Yes, so what we do with this is we counted a segment level error average to see what is the error evidence of each segment. That means how much percentage is the erroneous word happened in each segment by average, on average. Yes, so how did we counted this segment level error average? We counted by the total source text errors in words. So we counted by token number and plus total target text error numbers divided by total source text tokens plus total target text tokens. And from here, we can see how many words are erroneous according to our three annotators' annotations. So here we can see this column is segment-wise error average for any kind of error. That means all kinds of error. We got 0.279 for segment level error average score. That means 28% of the text has errors as annotated by the three annotators. That is about 1/4 of the 1/4 of the source, both the source text and target text, because the errors can happen on both sides. And for accuracy error, that is about 20% of the text has accuracy errors, and fluency errors has much less occurrence. That is about 7%, and style error has the lowest percentage, and critical error is similar to accuracy error. That is about 20%, and minor error is just about a little bit more than the fluency error. So from here, we can have some hint that we think accuracy error is kind of related to critical error, and the fluency error is more likely to be related to minor error. And we also calculate the weighted Fliss kappa for the inter-rater agreement, because as we can see from the last slide, among all the three annotators on the token-wise level, they disagree with each other a lot. But on the segment level, as we counted here, we see a very high agreement among all the three annotators on most of the error types. For example, we get almost 0.915 on the accuracy error, and similar percentage for the critical error. And for any fluency and minor error, we also get a very good inter-rater agreement, but it's just the style error, we get not that good agreement among the three annotators. And here we can see, we can assume that for the style error, the three annotators don't agree a lot with the annotations about style errors. Maybe they don't have good agreement on the definition of the style error, or maybe they don't have good understanding of what is a style error. That is my assumption. And also from this segment-wise error average score, the style error is very low. It's almost like 1% of all the tags in our data set has annotated as style error. So the annotators also didn't annotate a lot of style errors. That may be one reason for we don't get good agreement for the style error, or that can also be the cause of why they don't have a lot of agreement. They don't have a good understanding. Yes, and then next slide, we actually correlate the segment-wise error average scores among all the error labels. Here we can see that accuracy errors correlate best with critical errors and any errors. And it's a very strong correlation, as we can see from the score. And fluency errors, they correlate more with minor errors, and they have actually negative correlation with critical error and accuracy error. And for style errors, we can see as the same with the result from the last slide. It doesn't have good correlation with any kind of error in our error taxonomy. We think this style errors is a unsuccessful error taxonomy as our result shows. Yes, and then from this slide we can see that what we get a hint from the last slide, that accuracy errors are mostly critical errors and fluency errors are mostly minor errors. And this resonates with Michael's another paper in 2019. And if you want to read it, you can try to find it with Christina. And next slide. And here, when we get the segment-wise error average scores for each error labels, we can also see the relationship between the attention allocation patterns of the interpreters with their interpreting performance. These three attention allocation patterns, we have talked about it yesterday. We have eye dominant interpreter, ear dominant interpreter, and eye ear balance interpreter. Ear eye balance interpreter, actually. Yeah, so we think the interpreters tend to have these three kinds of attention allocation patterns as an interpreting strategy to relieve from the cognitive overload from this special mode of interpreting, which is simultaneous interpreting with text, because they have to pay attention to both channels, and it's a extremely cognitive demanding situation. So strategically, they tend to allocate more attention to one channel, or they allocate equal attention to both channels to avoid the overload of their cognitive resources, to their attention resources. That should be one method to improve their performance. So on this assumption, based on this assumption, we want to see how is the segment-wise error average scores can reflect or can have the relationship with the three types of attention allocation patterns. Here we can see we draw a box plot for error average any. So for the overall error numbers, we can see that for these three types of interpreters, if the box plot is more to the left, that means this kind of interpreters produce the least numbers of errors of this error type. And then if the box plot is more to the right, that means this kind of interpreter tend to produce more errors of this kind of error. Yes. So here, the first box plot is any error. So that is overall, we can see that I dominant interpreter, they produce the least errors according to our data set, of course. And then we can see that slightly different is the year dominant interpreters. They have a very big span of the box plot. That means they have a very large variation among the year dominant interpreters in regards with the any errors. And for the year I balance interpreters, we can see that this vertical line is the median of the error they produce, and this triangle, green triangle, is the mean value of the errors they produce. So we can see that year I balance interpreters, they actually produce the most errors among the three types of interpreters. So what we can conclude from this box plot is I dominant interpreters, they tend to produce the least errors uh, of the interpreting output, and the year I balance the interpreters, they tend to produce the most errors. And in terms of different error types, we aggregate the error average for the accuracy errors. We can see as the same as the last slide. And the I dominant interpreters, they produce the least accuracy errors than the other two types. And the year I balance the interpreters, they produce the most and the most various accuracy error among the three types of interpreters. And next slide. Yeah, and here this slide is the box plot for fluency errors. As we can see, it's quite different from the slide from the last slide. In terms of fluency errors, we can see the I dominant interpreter's box plot is the most to the right. So the I dominant interpreters, they tend to produce the most fluency errors among the three types of interpreters. And we can see that the year dominant interpreters, they actually produce the least fluency errors among the three types, and year I balance is in the middle. What we assume from this result is that year dominant interpreter, they tend to follow most to the flow of the audio input of the source text. Then they tend to have to some extent a deverbalization of the source text, and that leads to what we see here. From the result, they produce the least fluency errors. And the I dominant interpreters, they may get distracted by the written text, and this is called visual interference. And then this visual interference may lead to more fluency errors for the I dominant interpreters. And next slide. Yes, so what we conclude from our research from the last 2 days, yesterday and today, is we kind of observed that there are three patterns of visual or auditory attention for different interpreters as a strategy to avoid cognitive overload. We call them ear dominant interpreter, eye dominant interpreter, and ear eye balanced interpreter. Next slide. And according to the manual assessment of the simultaneous interpreting with text quality, we see that annotators do not always agree on error and identification for each word, but they arrive at a good inter-rater agreement on segment level. And higher inter-rater agreement on accuracy and critical errors were found in our dataset as compared to fluency and minor errors. And next slide. And the impact of dominance patterns on translation quality is that I-dominant interpreters tend to produce less accuracy errors because they follow most to the written text. And the ear-dominant interpreters tend to have less fluency issues because they follow the audio input and they follow the flow of the audio. And the interpreter's decision to allocate an equal amount of attention to both the audio and visual input, that is our ear-eye balance interpreters, could have a detrimental influence on the overall quality of the translation. Yes, next slide. And we also have some limitations for this study because as Dr. Feng yesterday explained, we have limited sample size. We get 9 participants and they are mostly professional interpreters. And we only have one language combination of interpreting, that is from English into Chinese. And next slide. And for our future studies, as we can see from the limitations from the last slide, we can look into additional language pairs. For example, maybe from English into Spanish or from English into Arabic. That is, we can get the participant maybe from Kent State. And the second one is we can, because in this research, we're looking to the highest ranking political speech, which is very complicated and very difficult source text. And all the 6 sessions are from the same source text, the same audio, just different clips. So we can actually look into other text types, or we can compare different text types for our experiment. And the third possible direction is maybe we can hire more participants, and also maybe we can replicate the experiment by comparing the translation process of novice interpreters to experienced interpreters. Because in this research, we only hired professional interpreters. Maybe we can hire some novice interpreters to see what is their difference. Next slide. Yeah, and here are some of our references. And thank you for your attention for this.
Okay, so everybody knows that we have this folder here under the CRITT guest account shared summer, and then we have all these different different notebooks that we already discussed. And for this session today, for the session yesterday, we have this this notebook that I already went through. Longhui was talking about 3 annotators: annotator A, annotator B, and annotator C. And they all annotate the same segments. They had 202 segments from 32 sessions. And this is all this interpretation data. And it just means we had a different study for each of those 3 annotators. And the only difference between those 3 studies is that they have different kinds of labels in the Yawat column. So if we load this table, then we can see here we look into the 3 first rows. Each row, then, as we can see here, is a segment. So this is the SG table. It means it's a segment It's a segment table. Each row then represents a segment, and we already went through all these features some time ago with duration and all these features for the various kinds of translation bursts and so on. And the thing that is interesting here is this column, Yawat. And so this is taken from the annotation. So if we look into, so this is the assessment from the annotator A, okay? And you can see that here, this third visit is annotated as a major fluency error, okay? And you can see there are two words in this error category here that show up in this alignment group. Here is a minor fluency error because it's a bit lighter, right? And here is a monolingual. So this is so these are by labels. So these groups are aligned, and then there's an error annotated. And this one here is an omission, and it's marked here as a major accuracy error. Okay, so that means if we look at the number of errors, error annotations in this segment, we see that there is two words on the left side here with this major fluency annotation, two words on the right side. So this is counts as 4 errors then. And these ones are 1, 2, 3, 4, 5, 6 major accuracy errors, which are only on the source side. And these again are 2 plus 3 here, 1, 2, 3, are 5 minor fluency errors, okay? So all these errors are accumulated and pasted into this column here. So we see here that this particular segment has is on the source side a coherence error, and well, remember that these labels here are only in the browser. Inside the labels, we would need to know what this coherence actually is. We could look into this JS script. So, but I assume this is a fluency error, maybe coherence error. And this, so we have these number of labels. So it's just the sum of all the error annotations from this segment here. And well, here, while we can see the browser version of these error annotations here in Jawat, we see, if you remember, the key of that hash that we annotated in that JavaScript. Okay, so each of these segments has a Yawat string, and then we can look into what is the distribution of these errors, and then we can just, with this command here, we get so we read all the stuff into one table, right? So this contains altogether 606 segments, 202 from each, but they are concatenated all into one table. So altogether, it should be 606 segments annotated, and then we can grab out this column from this table and count the values by with ascending false, means it starts with the most frequent error annotation. And here we can see this is the error annotation if there is no error in a segment. And so this means that 34 segments from the 606 don't have any error annotation. That is about how much? 5% or so, no? 5% of the segments have no error annotation. And then there are 7 segments that have this error annotation. So that means somehow an addition omission would be on that side, would be a mono label, right? Have this error annotation. This is on the target side only. And then if the string becomes longer, you can see that the number of occurrences becomes lower. So what we want to do, we want to split up this whole string into these atomic parts, into the individual errors, and count those errors. And this is done by this command. So again, this is another way. It's basically the same as this construct, and this construct is the same. It gets this column from the table here, and then splits the string at the plus, you see that all these arrows are concatenated with a plus in between. So if we split the string at the plus sign, then and we count the number of values, we can get this table here. So that means that basically, and this one here is then assigned to this particular table. It means that we have in this particular segment, which is segment 0, right? We have 4 cohesion or 4 arrows, whatever this cohes represents here. And 2 of this kind of arrow, 2 of this kind of arrow, and so on. Okay, so here we have split up all these arrow annotations into individual forms and counted them. And then what Longhui was talking about, this kind of any accuracy, fluency, critical error. So here, any error is just the sum of all these errors, right? So all the errors here in this segment would be any error. The accuracy error are specified here. So we have, these are the different types of accuracy errors on the source and the target side. The fluency errors are those kinds of errors, the style errors, those kinds of error, critical, minor. Okay. We can just generate new columns here, and then you will see here, these are the new columns. So we can see that this particular segment here, this number 0 segment, has 12 errors on the 2 sides. Remember, it's the source and the target side. Of these are 6 accuracy errors and 6 fluency errors, and 11 are critical and 1 is minor error. Okay, and these are then the kinds of error annotations that Longhui used and discussed in her presentation a little bit more. So we can take out those error labels here of interest, concatenate this back into the original table. So means here we have computed these errors that we are interested in. And this table here will have 606 rows, as many as the SG table. If you don't believe me, we can just insert below and we can just look for DF. Oh, I don't know whether. Okay, no, we don't do this because I didn't run the other cells. Okay, but so this has 606 cells and we just concatenate this stuff here with the original table, and then we can normalize this. Okay, so because each segment has a different number of tokens, we can normalize the number of tokens and or normalize the error here by the number of tokens, and then we get this table here where this is the original SG table. We get those so these error types here, and then we get their normalized versions here. And we can correlate the stuff, and you can see here that accuracy and any correlate size. So this is basically what Longhui showed, I think, these correlation tables here. And this is the correlation based on the normalized, so on the normalized version. So you can see here that it's slightly different and not as high. So for instance, here we have any influency 0.2, and here we have 0.04, and so on. This value change a little bit, but in principle,
I can explain. This is you use Pearson, Pearson, and I use Spearman.
Okay. Good.
Yes.
We can have a different kinds of correlation methods here. And the interesting thing that we didn't talk about was the correlation with these entropy measure. This HTOT value here, which is this guy here. This is the average word translation entropy of the translation. So that translation entropy Yusheng talked about, and this is the average, and we can see here that the accuracy and the critical errors correlate with the entropy value more than the fluency and the style errors. And this is the case even in the normalized, to a lesser extent in the normalized version here. But still, it's a weak correlation between the entropy values and the accuracy errors and the critical errors, but almost no correlation for the style and the fluency errors, right? Which indicates that, so this value here indicates the choice, the number of choices or the options, the translation options, the variation in the translation product. And it shows that if there's a much variation in a segment regarding the word choice, then it's more likely to have an accuracy error. And this is independent. So the fluency error basically is independent of how many translation choices there are.